In this lab, I analyzed the motion of a star orbiting a black hole in order to determine the mass of the black hole using Newtonian mechanics and computational modeling. The simulation generated a unique trajectory for the star based on a random seed created from my Georgia Tech email address that ensured that every student would have a slightly different orbit to analyze. The star in the simulation has a mass of 2 times 10 to the 30 kilograms, which is approximately the mass of the Sun. The black hole, located at the origin of the coordinate system, is located there and is assumed to be the only object exerting a force on the star. There are two parts to this lab. The first, analyzing a star's motion and determining the mass of a black hole, and the second, simulating a spaceship interacting gravitationally with both a planet and its moon, trying to create a stable orbit influenced by both bodies. The physics governing the motion of the star comes from Newton's law of universal gravitation. F equals gmm over r squared. The equation states that the gravitational force between two objects depends on the gravitational constant and the mass of the two objects, along with the square of the distance between them. Because the problem states that the only force acting on the star is the gravity from the black hole, the net force on the star must be equal to this gravitational force. And so by analyzing the motion of the star and calculating the net force acting on it, we can rearrange the gravitational force equation to solve for the unknown mass of the black hole. To calculate the net force acting on the star, the code uses Newton's second law, which states that the net force on an object is equal to the rate of change of its momentum. Momentum is defined as mass times velocity. Because the star's mass is constant, changes in momentum comes from changes in velocity. The position of the star was given at a set of x and y coordinates at equal time intervals. The time between each data point is 1 Earth day, which is about 86,400 seconds. By subtracting the momentum at 2 consecutive points and dividing by the time interval, the code calculates the rate of change of momentum. This quantity is then equal to the net force acting on the star. The program then separates the net force into two components, a component parallel to the momentum and a component perpendicular to the momentum. The parallel component changes the magnitude of the momentum, and the horizontal component, the perpendicular component, changes the direction of the momentum, but not its magnitude. In orbital motion, the perpendicular component is especially important because it continually redirects the velocity of the star towards the center of the orbit, keeping the star bound to the black hole. Once the net force acting on the star is known, we can use Newton's law of gravitation, rearranging it to find the mass of the black hole. Which, when I did with my seed, it was found that the average value was 1.95 times 10 to the 34th, simply taking all the different data points and averaging them out. The consistency between measurements suggests the computational method is working correctly, because and that the orbital data accurately reflects the gravitational influence of the black hole. The required discussion question, I already addressed that. Part 2 was the planet-moon spaceship system, throwing a spaceship in there. In Part 2 of the lab, I simulated the motion of the spaceship interacting gravitationally with both a planet and its moon. The planet was fixed at the origin, while the moon started to the right of the planet and moved in a circular orbit. The spaceship began on the surface of the moon and was given an initial velocity in the x and y direction, which for me was negative 700 in the x direction and 500 in the y direction, which led to this circular orbit, as you can see, or not circular, but elliptical orbit. For all objects, the forces acting on them are from both the other objects. It's a three-body system with the moon being interacted by the sun and the spaceship being interacted by the moon and the sun, which causes their orbits to shift slightly, and largely for the spaceship. The values of negative 700 and 500 were found through experimentation by trying different values and testing the orbits coming from them, with the goal to be a relatively stable orbit and a system where the spaceship doesn't crash into the moon within 700 hours, um, although this goes for about 4,000 hours because 700 wasn't showing enough data. If we wanted to predict the motion of the entire system realistically, which was the discussion question for this part, we would need to include gravitational interactions between every pair of objects, which would include interactions between the black hole and the star and the planet and the moon and the spaceship, and many others. In total, we would expect the forces to be the same, but the calculations would become much more difficult. For example, the moon's, and it's usually not necessary as the moon's motion is generally dominated by the planet's gravity and the planet generally by the moon, which would make the spaceships negligible, but we would be accounting for it and sort of going over the top. In conclusion, the lab demonstrated how computational physics can be used to determine properties of astronomical systems from motion data. By analyzing the star's trajectory and applying Newton's second law and the law of universal gravitation, I estimated the mass of the black hole to be approximately 1.95 times 10 to the 34th. In the second part of the lab, simulated the motion of a spaceship influenced by both a planet and a moon and determined an initial velocity that allowed the spaceship to orbit without crashing. The lab highlights how numerical simulations and physical laws can be combined to study complex gravitational systems. Thank you for listening.